Hi, and welcome to this lesson, which is metals and alloys, and it's the last lesson in the topic on structure and bonding. So your first task is to categorize these molecules or structures into their structure types. So pause the video while you have a go at that, then I'll go through the answers. Okay, so A, first of all, is a giant covalent molecule. You might recognize it as diamond. B are a load of simple covalent molecules. C is another giant covalent structure. D is another simple molecule, simple covalent. E is ionic, because you can tell by the positives and negatives on the particles. And F is metallic. Okay, our next task, again, we're trying to identify the type of bonding, but this time we're doing it via the properties rather than via pictures. So again, pause the video, try and work them out, and then we'll go through the answers. Okay, so when we're looking at A, the key feature that makes that different from all the others is the fact that it's got very low melting and boiling points. So what that tells us is that it must be a simple covalent molecule. Now B, C and D all have high melting and boiling points, so we can't really use that to distinguish between them. What we can use is their electrical conductivity. Now B is a good conductor of electricity, which suggests that it is metallic bonding involved. C is not a conductor at all, so that suggests it's giant covalent. And D only conducts when it's molten, so that tells us it's ionic bonding. Okay, so with the exception of mercury, all metals are solid at room temperature. Most have high melting points, and they are hard and rigid, malleable and ductile, and they're good electrical and thermal conductors. But some are better than others. They are harder, more malleable, have higher melting or boiling points or conductivity. For example, mercury is the only metal that's a liquid at room temperature. So there are different properties between the different metals. Choosing the best metal for a particular purpose may be a compromise between the suitability and the cost. Best is often most expensive. So for many purposes, no single element is suitable, so we use something called an alloy instead. And alloys are mixtures of metal elements, although some, such as steel, include non-metals. And steel is the most widely used alloy, and it's used in tiny items and massive construction. So the property of an alloy, you might expect it to be somewhere between the two elements, but that's not always the case. Alloys are usually useful because their properties are better than either of the single metal that's being used, and that's why they're more widely used than pure metals. So the well-known alloys, steel, which is made of iron, carbon, and some other stuff, some other elements. That depends on the type of steel. Stainless steel is steel with chromium and nickel, for example. Bronze is made of copper and tin. Brass is made of copper and zinc. And cupronickel is copper and nickel. And that's what we use in our silver coins, like 50p pieces, 10p pieces. Okay, so metallic bonding allows metals to be bent, pushed, and pulled into new shapes without breaking. Unlike covalent bonds, metallic bonds aren't fixed. Pure metals have regular structures. Their atoms are in nice rows and layers with the electrons in between them. Metals are malleable and ductile because of those layers that can slide over each other. And if we press or bend them, it changes the shape of the substance. It's a bit like clay or plasticine, but it needs more pressure. Okay, so if we apply a force, you can see the layers can start to pass over each other, and if we hammer it, therefore, we can hammer it out into thin sheets or pull it out into wires. Okay, and the alloy has had different size atoms added, which disrupts the structure and makes it more difficult for the layers to slide over each other. So it's much more difficult to flatten it out. Okay, it's harder and it's more rigid than its single metals, which means it's stronger but less malleable and ductile. So that's the reason we use most alloys. Steel, much stronger than iron, so more suitable for construction work and large objects. Bronze and brass bend and dent less easily than copper. Aluminium alloys are used for aircraft. Jewelry gold is an alloy. So if we had pure gold, 24-karat gold, it's too soft and it would kind of bend around on you and wouldn't hold its shape. So instead we use alloys of gold and copper, and that's either going to be 9, 14, 18 or 22 carat, and that tells us the ratio of gold to copper. So the lower the carat, the more copper is used in that alloy. Okay, metals have giant structures with metallic bonding between them, and the metallic bond is the attraction of the positive ions in their lattice structure with the delocalized electron C that surrounds them. So in order to melt a metal and allow the particles to move around each other, enough of those metallic bonds need to be broken, which requires a lot of energy, and so melting points are normally high. In general, when we have an impurity in a liquid, that lowers the melting point of that liquid. And alloys are made by dissolving one metal in another, so the resulting alloy has a lower melting point than either of the individual metals. Okay, that's not normally the reason for using an alloy, but occasionally it is. So for example, solder is an alloy of tin and lead and is used to make electrical connections because it melts easily. Some types of fire sprinkler use an alloy plug in the pipe, which melts when there's a fire, allowing the water to spray out. And of course, you can get a joke teaspoon made of something called Wood's metal alloy, which melts at 70 degrees. So if you put it into your tea or coffee to stir it, you lose your teaspoon. In terms of conductivity, metals are good conductors of electricity because of the delocalized electrons carrying electrical charge through the metal. And they're good conductors of thermal energy because the thermal energy can also be transferred by those delocalized electrons. When we add an alloy, when we add another metal, it decreases the conductivity because the electrons aren't flowing between straight rows. They're having to zigzag around the wonky particles, which means that they have to travel further. It means they take longer. For example, the electrical conductivity of brass is only about 1/4 of that of pure copper, but the reason we use brass for the pins of our electric plugs is because it's much harder. If we had copper and we tried to put the plug in the wrong place on the socket, it wouldn't go and the pin would bend and it would be annoying. Okay, that's why they make the pins much thicker. That compensates for the low conductivity. Right, let's have a look at some smart alloys.
Right, so what I have here might look like a normal spring and piece of wire, but in fact these are Shapememory alloys. So if I start with my spring, if I just compress that up nice and tight, you see that I can change the shape of it. And similarly with my wire, I am going to just scrunch that right up. Okay, so that's definitely not a straight wire, and I've got a nice flat spring. Now, I just pop the kettle on to get some hot water and get my Spider-Man mug ready. Okay, so what we're going to do is we're going to see the effect of heat on these Shapememory alloys. Okay, so if I just pour myself a spider mug of hot water, and let's start with popping the spring in. Now, it's gone in not at a great angle there, but it has expanded in the water back to the shape it was in previously. And then I will do the same for the wire, and you see immediately that springs back into its normal shape. Okay, if I wanted to fix the shape of these as anything other than what they are now, I would need to shape them at a temperature of about 500 degrees, and then they will hold that shape, and that's the shape that they will return to if they are heated gently to like 70 plus degrees. This is really useful for things like glasses where you want the frame shape to return back to normal if they're damaged.
Okay, so how does it work? Why do smart alloys do this? How do they go back to their original shape while heated? Well, what's happening is the crystalline structure is temperature sensitive, so the crystals revert to their original structure.